Let's dive into the world of graph optimization with an introduction to the minimum spanning tree, often called MST. A minimum spanning tree is a subset of edges from a connected, weighted graph that connects all the vertices together. It achieves this with the minimum possible total edge weight, and importantly, it contains no cycles. Think of it as the most efficient way to link all points in a network. Minimum spanning trees have several key properties. For a graph with n vertices, an MST will contain exactly n-1 edges. It is acyclic, meaning it forms a tree structure without any loops. The MST minimizes the total weight of all the edges included. A graph might have multiple valid MSTs with the same minimum total weight. MST follows the cut property, which means the lightest edge crossing any partition of the graph must be included in the MST. Minimum spanning trees have many real-world applications. In network design, they help minimize cable length in computer or electrical networks. In transportation, they are used for road or railway planning to connect cities with the minimum total distance. They are also used in data mining and classification algorithms for clustering. Additionally, they can minimize total pipe length in water or gas distribution for plumbing and pipeline projects, and minimize wire length in integrated circuits for circuit design. To work with minimum spanning trees, it's important to understand how to represent graphs in a way that algorithms can use. Two common representations are the adjacency list and the edge list. In the adjacency list representation, the graph is represented as an adjacency list with weights. For each vertex, we store a list of its neighboring vertices along with the weight of the connecting edge. This representation is efficient for sparse graphs and many MST algorithms. In the edge list representation, the graph is represented as a list of edges. We store all edges as tuples containing the source vertex, the destination vertex, and the weight of the edge. This is particularly useful for algorithms like Kruskal's, where sorting edges by weight is a key step. Kruskal's algorithm is a popular method for finding the minimum spanning tree of a graph. The basic steps involved are as follows. First, sort all edges in non-decreasing order of their weights. Next, initialize the result MST as empty, and create disjoint sets for each vertex. Then, for each edge in the sorted order, check if including this edge creates a cycle in the MST. If no cycle is formed, include the edge in the MST. Repeat this process until the MST has n-1 edges, where n is the number of vertices. The time complexity of Kruskal's algorithm is typically O of E log E or O of E log V, where E is the number of edges and V is the number of vertices. The space complexity is O of V plus E. The key data structure used in Kruskal's algorithm is the union find, also known as disjoint set. Here's a Python implementation of Kruskal's algorithm. We first define a disjoint set class, which includes the methods required to find an element and perform a union. The init method creates a parent array to store the parent of each node, and a rank array for the union by rank optimization. The find method finds the representative, or root, of the set. Path compression is used to make every examined node point directly to the root, improving efficiency. The union method merges the sets containing X and Y. Union by rank optimization attaches the smaller rank tree under the root of the higher rank tree, keeping the tree relatively flat. The Kruskal_MST function takes the graph, represented as a list of edges, and the number of vertices as input. It creates a list to store the resulting MST. Sorts the edges by their weight using a lambda function. Creates a disjoint set for each vertex using the disjoint set class. The algorithm keeps adding edges until the MST has vertices -1 edges. It checks if including the current edge creates a cycle by finding the sets of the two vertices. If the sets are different, it appends the edge to the result and merges the sets using the union method. Let's walk through an example of how Kruskal's algorithm works. Starting with sorting the edges, let's assume we have edges with the following weights 1, 2, 4, 5, and 7. So the edges are C to D with weight 1, B to D with weight 2, A to C with weight 4, B to C with weight 5, and A to B with weight 7. Now we add edge C to D with weight 1 and no cycle is formed. We add edge B to D with weight 2, and again no cycle is formed. We add edge A to C with weight 4, and no cycle is formed. We skip edge B to C with weight 5, because adding it would form a cycle of B, D, C, and B. We skip edge A to B with weight 7 because adding it would form a cycle of A, C, D, B, and A. Thus, the final MST includes edges C to D with weight 1, B to D with weight 2, and A to C with weight 4. The total weight of the minimum spanning tree is 1 plus 2 plus 4, which equals 7. Prim's algorithm is another classic algorithm for finding the minimum spanning tree of a connected, weighted graph. The steps are as follows. Start with any arbitrary vertex as the initial MST. Initialize a priority queue with all edges from the starting vertex. While the MST doesn't include all vertices, select the minimum weight edge that connects a vertex in the MST to a vertex not yet in the MST. Add the selected edge and vertex to the MST. Then, update the priority queue with edges from the newly added vertex. The time complexity of Prim's algorithm is O of E log V when using a binary heap for the priority queue. The space complexity is O of V plus E. The key data structure used is the priority queue, often implemented as a min heap. Here's a Python implementation of Prim's algorithm. We begin by importing the heap module for heap-based priority queue implementation. The prim_MST function takes the graph, represented as an adjacency list, and the number of vertices as input. Starting with the first vertex, 0, we initialize an empty list, MST, to store the edges of the minimum spanning tree. We maintain a Boolean list added to track which vertices have already been added to the MST. We initialize a priority queue, edges, using heap.heapPush. We add all the edges from the starting vertex to the priority queue. The main loop continues until the MST includes vertices minus 1 edges. It retrieves the minimum weight edge from the priority queue. If the destination vertex V is already in the MST, it skips this edge. Otherwise, it adds the edge UV weight to the MST and marks vertex V as added. It then adds all the edges from the newly added vertex V to the priority queue. The function returns the MST, which contains the edges of the minimum spanning tree. Let's work through an example of Prim's algorithm in action. We start with vertex A as our initial MST. Add edges from A to the priority queue. The edges are A to B with weight 4, and A to C with weight 3. We extract the minimum edge, which is A to C with weight 3, and add C to the MST. Add edges from C to the priority queue, C to B with weight 5, C to D with weight 2, and C to E with weight 6. Extract the minimum edge, which is C to D with weight 2, and add D to the MST. Add edges from D to the priority queue where D to E has weight 1. Extract the minimum edge, D to E with weight 1, and add E to the MST. Extract A to B with weight 4, and add B to the MST. Thus, the final MST contains the edges A to C with weight 3, C to D with weight 2, D to E with weight 1, and A to B with weight 4. Let's compare Kruskal's and Prim's algorithms for finding minimum spanning trees. Kruskal's algorithm is edge-based and processes edges in order of their weight. Prim's algorithm is vertex-based and grows a single tree from a starting vertex. The time complexity of Kruskal's algorithm is O of E log E or O of E log V. Prim's algorithm has a time complexity of O of E log V with a binary heap. The key data structure for Kruskal's is disjoint set, also known as union find. For Prim's algorithm, the key data structure is the priority queue, typically implemented as a min heap. Kruskal's algorithm is better suited for sparse graphs, where the number of edges E is much less than V squared. Prim's algorithm is better for dense graphs, where east is close to V squared. Kruskal's algorithm is generally simpler to implement than Prim's, which involves managing a priority queue. Kruskal's algorithm stores sorted edges and a disjoint set, while Prim stores the graph representation and a priority queue. To conclude, use Kruskal's algorithm for sparse graphs and when simplicity is valued. Use Prim's algorithm for dense graphs and when growing a single tree from a specific starting point is preferred. Both algorithms guarantee a correct MST, but they may produce different trees if multiple MSTs exist with the same total weight. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.